Yeah. Um, just so we know that we won't be diving into TensorFlow in this session. This is just to get just to learn the ropes of all the machine learning techniques and theory you need to know. And starting from our second lesson on, we'll be using TensorFlow and TensorFlow Playground to build some neural networks. So, uh, just a heads up, this isn't a lecture. These resources are from the AI experts at Google, and they're designed to cover all the important aspects of machine learning you need to know to use in industry. And yeah, so let's get into it. So first up, we have this video by Oxford Sparks, and it just gives a brief outline of machine learning. There are a couple videos scattered throughout this presentation. I promise they're short. Give me a second. I couldn't get the audio working with the video, but these slides will be uploaded later on. So this YouTube video you should be able to find. But the main overview of the video is how we define machine learning as a specific field of this broad umbrella word, artificial intelligence, where a system learns to find patterns in examples in order to make predictions. So what they were trying to cover in this video was how, much like an infant, a machine learning algorithm learns through patterns as opposed to learning a set of rules, and computers learn how to do a task without being explicitly programmed um, in machine learning. So that's basically the gist of what this video covers. And next up, there is this short game called Google Quick Draw, which is again, you'll be able to access this in the slides, but the main way the game works is it gives you a word and you need to sketch out a diagram. Oh yes, Stelios put the link in the chat, so have a couple minutes to play around the game. Yeah, but the main objective of the game is to draw the shape you're told to, and the computer will quickly guess what it is you're drawing, and it's pretty quick. So yeah, I'll give you guys a couple minutes to play around with that. It's really quick and it's pretty fun. In the next couple slides, we're going to talk about how it is QuickDraw works, and what QuickDraw really was a neural network in action. So you could really see the finished product right in front of you, and I think it's good to look at the finished product right before we learn how to code it. So if everyone's have a had a quick go with that, we can move on to start asking a few questions about QuickDraw. So, how exactly does the game work? How is it recognizing your drawings? And how could we program this? So, if anyone has any ideas, feel free to drop it in the chat. But yeah, these are the main questions we're going to be looking at throughout this first lesson. So, how the game works, how can it recognize your drawings, and how could we program this? Um, Train it with loads of bad drawings and of things. Yeah, definitely. Something I noticed when I first started playing around with it was it it picked up the drawing before I finished it, so which meant that it's able to recognize the pattern from partially completed drawings, so it doesn't need the full pattern to recognize the drawing, which I found pretty cool. But yeah, as they mentioned in the chat, um, a lot of poorly drawn drawings go into making this machine learning algorithm. So this is what we call the training set, as in it's just a set of data we use to train um, the algorithm, help it recognize what is a carrot, what isn't a carrot, and go on. And yes, there is a large amount of data used to teach this game on how to recognize images. So if you were going to describe what a carrot was to someone who had never seen it before, using only these images, how would you describe it? So I'd go for features like the shape of the carrot, triangular tip, the bushy green bit on the top, and yeah, so it's basically um, the computer figuring that out for itself. And in conventional programming, which is rule based, you'd be really familiar with traditional programming, where you start with a goal and you write logical rules um, that you refine throughout testing. And that's how traditional programming works. You know where you want to go, you write the rules to get there. Now, imagine if you had to describe a carrot the way you just described using traditional programming. So, such as those rules on the right side of the image. So, like a bunch of if statements. This process would get very complicated, especially if you wanted to account for all the possible ways one could draw a carrot. So, this doesn't really. So, for tasks like trying to identify a carrot, traditional programming doesn't really work well, and it could be pretty slow and space and time consuming. But the machine learning approach is a bit different in that it's an alternative approach to building software. So instead of the programmers creating the rules, the model is trained with examples rather than trying to define for the computer what a carrot is and account for all of the possibilities. The computer is given lots of varying examples, like you saw in the quick draw data, and told this is a carrot, this is a carrot, this is a carrot. This this approach results in a more flexible understanding for the computer, because um, it's able to learn from the real world rather than going through a bunch of if statements, which is pretty time consuming as well. So some questions you might ask is, what might be a limitation of this machine learning approach, or what types of tasks do you think would be a good fit for machine learning? Because this way of going about solving a problem doesn't necessarily work for all tasks, and we're going to see more of that later. And an example of where machine learning models are good is, for example, if all of the examples are triangle shaped, it may fail to recognize a rectangular shaped drawing as a carrot. So now we're going to go through some quick real world problems and try to decide if rules based learning or machine learning is the optimal solution. So, say we needed to alphabetize a list of song titles. What do you guys think would be better, rules based or machine learning? Yeah, quite a few people have said rules already, and yeah, that is the answer because there are already a bunch of sorting algorithms that are specifically designed for sorting lists, and if you think about it, there's a finite number of alphabets, so there's only so many rules you have to write. Um, what about ranking web search results? So this is a tricky one because it depends on the context. Yeah, Nicholas said rules. Yeah, there's a mix of rules and ML, and the answer is well, you could use either of them. It's a trick question. Um, the approach you take would depend on your end goal. So, if are you ranking web results based on relevance to my query, or if the query was news, you might also want to take into account how recently the article was posted. So, there's a bunch of rules you need to account for, and while implementing the ML, and yeah, it depends on what you're ranking. That's right. What about predicting house prices based on location? Yeah, I'm getting ML in the chat, and yeah, that is pretty much the answer because it's for things like predicting stuff based on some parameter variable like location. Yeah, regression's a great example. We're gonna dive into that in a bit, but it's like there's no perfect formula to determine how much a home would cost based on its location. So, and there are a bunch of factors that could play a part in the low price cost. So something like regression would give you a great continuous output. And processing online payments. What do we think about that? Rules based on machine learning. Yeah, I'm getting a bunch of rules in the chat. Yeah, it is rules. The reason why we go with rules based is because online payments are a straightforward, well, well, not straightforward, more like a logical process. Like there's a you can plot out a flow chart of what you want to do in an online payment process, and it is possible for a programmer to confidently program the exact steps necessary. But fraud detection, which is a component of online payments, could be improved by machine learning because you can use it to know whether a credit card number was stolen or used inappropriately. And that's a much more complex problem to define using rules. So, yeah, the answer was rules. And the very last one, classifying an object in a photo. Given we did quick raw, this is, yeah, it's pretty much ML. Because there's too many variables to account for in every situation. No two photos are alike. Um, and yeah, machine learning would be the most flexible and best approach for this, to be honest. So a quick recap: rules-based approach, the rule-based approach, are the ones where rules are defined, and if improvements come from algorithms and network. Machine learning, on the other hand, is where the system learns patterns from data, and improvements can be made using additional data. So machine learning will not become the default option for software. It is best suited for certain but not all situations, and that's important to know when we need to use ML. We can't just throw it at any problem. Now we're going to go over some ideas to implement that we can implement using machine learning. So while machine learning offers powerful new opportunities, implementing an ML system can be more complex than traditional software. This is primarily because a machine learning system is only as good as the data it's trained on. In this section, I'll provide an overview of the process as well as the important considerations we need to take into account. So there was meant to be another video here, but unfortunately I couldn't get the audio up and working. So the gist of this video is covered in the next slide, but obviously it's a great idea to have a look at this video when the slides are released. So this is an outline of the machine learning process. So machine learning begins with the needs of your user and business. Bearing this in mind, you need to define an objective so you know how to proceed. Examples could include to predict which friends a user is likely to share a photo with, or suggest the user should eat in a new city based on restaurants they've visited in the past. So again, learning from previous data to make future predictions. And these goals should articulate success metrics as well. So there needs to be some way of measuring how good we are to achieving what we want. After we define the objective, it's data collection. So machine learning models learn from examples, so it's essential to find a large existing source of data that's relevant to your problem. So experts say collecting, cleaning, exploring, and other data processes um, explore exploring and other data processes tend to be the longest but most critical part of the process. Um, Now, for part four, testing and training the model. So the arrow pointing, um, testing and training the model is is what you do after you collect the data, pre-process it, and get it through all those stages. An important thing to note is this arrow over here. Um, so the arrow pointing back from prediction of the arrow pointing back from prediction to the data shows the iterative nature of ML. So you will need to refine your model and perhaps your data collection and processing based on the feedback until it's achieving the results you're looking for. So these two arrows over here are really crucial to the machine learning process because it shows that it's an iterative process. The model keeps learning until you realize, yeah, until you hit the point where you realize any more learning wouldn't be worth the time when you weigh it against the improvements you get. So again, there's another video here on machine learning and human bias, which just talks about how humans are prone to trust results from a computer, and how we assume our technology will work as it's designed until it breaks. So um, the main thing this video was trying to get across was how even a well-designed machine learning pipeline can experience issues when it picks up on biases found in data. So all it's trying to say is there will be problems and there is bias. It's a great video to have a watch. And This is another video talking about machine learning privacy. Unfortunately, I couldn't get it to work in terms of audio, but um, yeah, the audio still doesn't work. So the main points from this video is you need to it's trying to tell you how a machine learning system needs data to achieve its goals, and the less data you have, the less you need to protect. But that also means you don't have enough. If your training set is too small, it might be too generalized, as in it won't work very well for specific cases. So it's really a trade-off between having a lot of data to train your model well, but also having to account for GDPR regulations and data privacy. Next up, what can machine learning do? So it's easy to look at examples of machine learning and see it as magical, like the Google Quick Draw, and it does open a lot of new possibilities with technology. We already considered for certain situations whether machine learning was necessary. In this section, we will discuss what type of problems machine learning is best suited for. So this is an important Venn diagram because it shows you what each of the buzzwords mean. So in news and article discussions, it's common to see artificial intelligence, AI, machine learning, ML, and deep learning, DL, used interchangeably, but there are some important distinctions between them. So artificial intelligence is the broadest term, and it encompasses all of what we're going to talk about. It's defined as any technology which appears to do something smart. And that's a very vague definition, but the way I think of it is it has a set of rules which it uses to think for itself, as in it's only given the axioms and it's going to draw implications from the rules you give it. And this can be anything from program software to deep learning models which mimic human intelligence. So artificial intelligence is a very vague definition, and it's been around. I think it was first coined in the 1950s, so it's been around for quite a while. Now, machine learning is a subset of artificial intelligence and is a specific kind of artificial intelligence. Um, but rather than a rules based approach, the system learns how to do something from examples rather than being explicitly told. So it's a bit more niche than artificial intelligence in the fact that it figures out what it's supposed to do on its own. Like you don't have to explicitly tell it; it learns from patterns it sees. And deep learning is an even more niche category of machine learning, um, which is a specific type of machine learning used in a technique known as neural networks, which connects multiple models together to solve even more complex problems. So the way deep learning works, and we'll dive into deep learning a lot in the next lesson, um, it has this layered approach where it makes decisions based on um, based on passing inputs through different layers, and each layer behaves similar schematically to a biological neuron, and that's why hence the name neural network. So deep learning is similar to a lot of ML models, as in it learns via examples, and it's unique because it connects models to other models in layers in order to handle more complex tasks, such as like images. And yeah, so machine learning, um, it is it is a pretty handy technique, but it's a crossover of many important computer science concepts, which which a lot of people have studied either in school or at university modules. And that brings us to this very simplified overview of the history of machine learning. You can find more detailed timelines on Wikipedia, but here's the main takeaway. The key algorithms powering machine learning were formulated as much as centuries ago. They come from disciplines like statistics, linear algebra, biology, and physics. Over the last few decades, sufficiently large amounts of data were collected to train models, but they were low quality and expensive to train. So, lack of progress and prospects led to an AI winter where machine learning was considered a waste of time. In the last few decades, however, the availability of relatively cheap data and fast computing power have enabled complex calculations across large sets of data necessary to train highly accurate models. So that's a brief summary of um, all the machine learning that's happened so far. So I think now we're going to go over some machine learning algorithms, like the actual algorithm, how it decides and makes decisions. The first and most simple one is called classification. So classification is a common application of machine learning where the system determines which class or category an example belongs to. The output can be labeled as a percentage of confidence. So it gives you a discrete output, yes or no. Is it lion? Is it a lion? Is it not a lion? Stuff like that. So, for example, if the classifier were trained to identify whether or not an image was of a lion, it could output yes or no. Or you could make it a more general animal classifier, and the output could be lion or tiger. So classification systems depend on a threshold set by human developers, so the system can distinguish between cases that may be less clear. So if you built, say, an email spam classifier, it would be necessary to fine tune the threshold so your system didn't incorrectly label an email as spam um, when it was genuine. So the machine does the classification, you just fine tune the parameters, and you'll find that as a recurring theme in a lot of machine learning. Next up is an algorithm called regression, which was mentioned earlier by Temi in the chat. And regression is a system that outputs a number. So instead of outputting a category like classification, it gives you a continuous variable number. So regression systems output a number, for example, how long it takes to drive from point A to point B, or the likelihood that someone was going to click on an ad. So regression systems can be as simple as drawing a line, as you see above, or more complex depending on multiple variables. So in the simplest case of this line, it's literally just plotting the data points in a scatter graph and figuring out the line of best fit. That's that's a machine learning algorithm. Machine learning's been around for a while, so a lot of simple techniques which we take for granted are in fact machine learning. Next up, this one's a pretty interesting one, which I like quite a bit, and it's called clustering. So clustering is another application of machine learning, um, and it determines how closely related items are to one another. So in this slide, the data of hand-drawn images is moved into clusters of the same number, ones with ones, twos with twos, threes with threes, etc. Even within the clusters of the same number, the images are further clustered into those which are similar in shape. For example, some twos and sevens may look similar. So again, if you think of trying to do a task like this using rule-based traditional programming, it would take ages. Uh, and yeah, this clustering diagram was from Google, so it looked pretty cool. Another example of machine learning is sequence prediction. So in order to assist users, it can be helpful to predict what they might do next. This could be a prediction of the next keyboard key a user will select, as you see in the screenshot. This could be used to propose a spelling correction or suggest replies to a text message, so basically autocorrect. Other examples of sequence prediction could include what's covered in the next video, where a user wants to plan a vacation. But we'll skip the video for now and move on to the next one, which is style transfer. So style transfer is sometimes so this is another pretty cool one where it combines aspects of two sets of data. It's sometimes called generation, and it involves training a model on one set of data, then applying that model to something completely different. So it could be seen in this example of remaking photographs to look like another piece of art, or translating a voice from male to female, or even to another language. So now that you've seen a few examples of machine learning, let's go through some examples, and you tell me which type of machine learning best describes it. I say best because some problems can be solved by multiple approaches to machine learning. So, say we wanted to recommend what someone will download based on previous purchases. What do you think works best here? The key to this question is based on previous purchases. I see clustering pop up a bit. Well, the answer is actually sequence prediction, because it's based on previous purchases. So it looks at the history of what was previously committed and tries to guess what's the next best thing that can be done. So while all examples of machine learning involve previous examples, this is an example of predicting the next thing a person will do based on previous or similar sequences the model has learned from. So this was a pretty hard one to begin with, to be honest. What about labeling email as spam or not spam? So we're trying to decide whether email lies in one of two categories. So yeah, as the chat's saying, it's classification. Um, because when the goal is to output a discrete prediction label, like yes or no, spam or not spam, this is a good fit for a classification system. How about identifying trends among a group of people who have bought a new music release? So it involves a group of people. Yep, I see a few clusterings in there. Yeah, I think it's clustering too. The reason it's clustering is because the goal for this problem is less about making a specific prediction, like sequence prediction, but looking for similarities and finding clusters, trends, groupings based on something in common. So I think the key giveaway here was the fact that you're dealing with a group of people. So when you're looking at characteristics that bring groups of uh, people together, it's clustering. Quick question: can classification only classify between two discrete options, or can it be more than two? Um, that's a good question. Classification. So the classification they presented here does work with two options, but I believe you can do more than two. Except there's a different name for that. I think it's called categorization or one-hot encoding. I can't remember the exact name, but I'll get back to you on that. Um, Now, captioning a video. So, say you had a machine learning model that automatically generated a caption for a video. Which type of category would that fall into? I found this to be a pretty hard one when I first looked through the slides. Yep, Jan said style transfer, and yeah, it is style transfer, in fact, because when the type of data generated by the system is different from the input data, it's an example of style transfer. So the input data is a video, and the output data is a text. So, oh, you're applying what you learned from looking at a bunch of videos to outputting a text. It's just like how in the previous image we looked at a bunch of artworks and applied it to a photograph. So in this example, the input data is video and translate the text. Now, this one is determining workout activities based on phone movement. Clustering. Regression. Okay. So I can see why you'd think regression because phone movement is a continuous variable, but at the end of the day, we're deciding a workout activity, which can be one of a bunch of specific categories. So this is in fact classification. And Nicholas, this is an example of where classification decides between more than two categories. So the goal is to put output discrete labels such as walking, running, jumping, and a bunch of other tasks to make a good fit for classification. Next up, predicting the strength of a password. So over here, we're trying to decide what the answer. Okay, so I'm seeing a few regressions. Okay, that's good. So this one can actually work in two ways. It could be regression or classification. It depends on how we decide how strong a password is. So when the output of the machine learning system is a continuous number, such as your password is stronger than 40% of others, that's a regression problem. However, your users might prefer if you take an output and simplify and simply classify it as weak or strong. That's an example of a classification algorithm. How about identifying famous landmarks in a photo? So we're trying to come up with a label for a famous landmark. So it's trying to look at a photo and decide what it is. Yep, I see a classification. Yeah, this one's classification. Because when the output is a discrete label, like the Eiffel Tower, the Taj Mahal, Great Wall of China, it's a classification problem because your output can be one in a set of finite categories. And we've got a few more questions like these. I guess got to power through them. Suggesting spelling corrections. Yeah, I'm getting sequence prediction, and yeah, sequence prediction is an answer because a lot of it wasn't. It was even one of the examples used in sequence prediction. But I think this slide also wants to highlight that clustering can also be an acceptable answer. I agree that sequence prediction is also an answer, but the reason why the slides are saying clustering is because it's a useful approach for this problem because misspelled words tend to be closer to the intended words. So if another word, um, so also if another word entirely was intended, so like advocate, advocate, the English and French versions of them. So when you have a small error like this, I'm trying to think of a way to explain them, but it's mostly like when you can cluster together words which are misspelled and they may end up closer to the correct spelling than a completely different word. So it's like when words are like only one letter off, you can group them to be close together, and we can associate everything in that cluster to one correct word, advocate, but it does have its downfalls, which is why I think sequence prediction is also a good answer. So next up, predicting the quality score for an advertisement. So the quality score will be a number. So it would look at an ad and come up with a number as an output, and yeah, regression, that's the answer. Because when your output's like a continuous number, regression's the way to go. Okay, so we've got a couple more left. Estimating the arrival. Oops. Okay, so these already had the answers in, but estimating the arrival time based on the time of day and traffic, that would be a regression because, again, you're estimating a continuous number. And lastly, translating between two languages would be style transfer because although both of the input types may be text or audio, the languages are different. So this is important to note because a translation model trained for one language could be retrained to translate between other languages. So some translation tools use programmed rules to translate from one language to another, but increasingly um, increasing the quality requires time to grow. So languages may not have clear rules for translation between languages, such as French and Mandarin Chinese. So using style transfer helps pick up on the patterns from one language and essentially carry it over to another. And yeah, that's it for this session. So if you have any questions, feel free to drop it in the chat. But the most of the things we've covered so far are the fundamentals for machine learning, which hopefully we can carry over to our next session, um, and use to make a neural network. So thanks everyone for coming. If you have any questions, drop it in the chat. We finished earlier than expected, but that's mostly because I didn't have time to go over the videos. Sorry about that. Hopefully you guys can have a look at the videos. The slides should be on our Durham DSC page. But yeah, thank you all for coming. Hope you enjoyed.